Okay, I thought we'd go ahead and go over the solutions to the quiz here. See if I can get this refocused here just a little bit. Okay, all right, let's go over number one together. It says find a parametric form for the line through these two given points. Use arc length as a parameter. Okay, what I'm going to do, it doesn't matter which direction you're actually going, from P to Q or Q to P. I'm going to do this, though. I'll go from P to Q just alphabetically. I'll go U is the vector from P to Q, so I'll put an arrow that way. Okay, and then this is going to be the following. You're going to obtain that vector. Okay, so we use the angled brackets. We're going to just take the difference between the corresponding coordinates of the points. So that's going to be 2 minus -1 is 3. Okay, 7 minus 1 is 6. Okay, and -5 minus 3 is -8. Okay, so this is what? That's a vector parallel to the line we seek. Okay, that's parallel to the line we seek. And now, because I'm going to use S, which is arc length as parameter, what I need to do is actually find U hat. Now, whenever I put a hat on a vector, I mean that's a unit vector, right? Okay, that means that's the direction vector, or that vector divided by its own magnitude, right? So it'd be parallel to this original, but have a magnitude of 1. So what we need to do is compute the magnitude of this thing. Okay, we know how to do that. That's pretty easy. That's the square root of the sum of the squares here. Okay, the square of the 3 is 9. The square of 6 is 36. And the square of 8 is what? 64. Okay, so this is what? 109, is it? Okay, and I'm not sure we can do anything with that. 109, I think that's prime. So let's go ahead and do this here. Let's talk about the position vector in just a second here, but let's do the U hat. So what I would do is take this vector and divide it by that. So it would be this. You can leave that scalar on the outside. Some people do. Okay. All right. Now let's go ahead and write this in vector form here. I'll go like this. Any particular point with would yield a position vector xyz. So any particular point xyz would have position vector xyz with the angled brackets. Take the position vector of either of the starting points. Probably P is the most logical one for the way I started here. And then what? Any multiples of U hat. Okay. Okay, so this would be one way of writing it. There I've got a vector form. You could break it down and do stuff like this. -1 plus 3t over the square root of 109. Y equals 1 plus 6t over the square root of 109. And z is equal to 3 minus 8t over 108. Okay. Oops, I shouldn't be writing t, should I? I'm sorry. You guys probably caught me. This should be s here. We reserve arc length for s. Okay, so I should really call that s there rather than t. So I'm going back. I don't like the way I make my s's here. They look too much like 5s. But anyways, since I'm talking here, we know what we're talking about here. Okay, s is any real number. All right, so there's the solution on that one. Okay. maybe I should move just a little closer to the camera here. It's looking a little blurry to me today for this. Okay. All right. Find a normal form for the plane containing these points. So we've got the following points. We've got P, Q, and R. Okay. I'm going to create my first vector, and I'll go from P to Q. Okay, so I just take the difference in the coordinates here. So that's 4 minus 0, so that's 4. Negative 1 minus 1 is negative 2. 2 minus 1 is 1, so that's one vector. Okay, that vector is actually what? Parallel to the plane here. Okay, V, I'll go from maybe P to R, and that will be 3 minus 0 is 3. 3 minus 1 is 2. 7 minus 1 is 6. Okay, so this is also parallel to the plane. Okay, now if I go ahead and take the cross product, again, the order doesn't matter on these things. If I take the cross product of these two, okay, I'll use IJK notation here, but when I get down to my vector, I will just use the component form. Okay, I'm going to go U cross V, and I'll maybe give that a name here. Let's pop that out here, make it a capital here. Okay, N, what is N? N is a normal, right? It's orthogonal to every vector parallel to the plane, right? Okay, so that's going to be the normal for the plane. Let's take the cross product, okay, and let's be careful here. Okay, so it's like taking a determinant there on this part. We're going to go like this. We're going to go what? Negative 12 minus 2. That's negative 14. Okay, when you're doing the middle one, be careful. You're taking your products, or your differences of your products, in the opposite order. So that's 3 minus what? 24. So that's 3 minus 24 is what? Negative 21. Okay. All right, now positive. Okay, we'll talk about checking this here in a second. Anyways, let's come back up here. And then here, we're going to do it this way, right? Back to normal. 8 minus negative 6 is 8 plus 6. That's what? 14, positive 14. Okay. Now, before I go on here, I'm gonna maybe say that's N1. Okay. Now, any vector parallel or anti-parallel to this is going to be what? Also be a normal. You must notice that each one of these is divisible by what? 7 or even minus 7. I'll factor out minus 7 here. So the normal I'm going to use is not this one. The numbers are too large for me. I'm going to divide out negative 7, and I'm going to get what? 2, 3, negative 2. Now if I did everything right, this should be a normal for the plane I seek, right? Now, to just double check and see if I'm right here, what I'm going to do is take what? A dot product of this normal n with each of these vectors here, and I should get 0, right? Okay? Because that would imply that these are what? Orthogonal in each case. Okay? Let's try it. Let's go. 8 plus negative 6 plus negative 2. That is 0. It is. Okay, let's do it on this guy. 6 plus 6 minus 2 6s is 0 also. So this guy is going to be important for me. That's going to be a normal. Okay? Now remember, the idea is I've got this normal to the plane here. Okay, so let's say here's my plane. Hope you can see that. And this is my normal. And I'll take a point on the plane. How about the point on the plane I start with is P there. And if I have any arbitrary point x, y, z, the vector from P to x, y, z lying on that plane should be what? Orthogonal to n. Okay? And in fact, it's the locus. The plane is the locus of all such points satisfying that condition. Now, the vector from P to x, y, z would be what? X minus 0, which is x, y minus 1, z minus 1. And when I dot with that with n, I should always get 0. Okay, I'm sort of running it in there. Okay, So let's see what it looks like. 2x plus 3y minus 3 minus 2z plus 2 is equal to 0. Okay, if I did my arithmetic correctly, let's make that more 2-like. Let's go like this. 2x plus 3y minus 2z equals, well, negative 3 and 2 is negative 1. If I move that over to the other side, I would get 1. And remember, this is okay to leave it this way, but just for emphasis this one time, it's a set of all points x, y, z such that 2x plus 3y minus 2z is equal to 1. Okay, how would you check your answer? Well, you would take each of the points that you were originally provided and plug them in here and see if it works. Does 0, 0, 1 satisfy here? 0, 1, 1. 0, 1, 1, yep. 4, negative 1, 2. 8 minus 3, yep, that looks good. 3, 3, 7. 6 and 9, 15 minus 14 is 1. Yes. Okay, so I'm going to box in my final answer here. I like you to box in your final answers so I see what you're asserting here. I guess I should have done that in the previous case, but it's spread out, but it's pretty clear here. Okay, so there's number 2. Find the coordinates of the point of intersection of the line with the plane here. Okay, hold on just one sec. Hey, here's our calculus, folks, sitting right here. Let's lift this maybe a little closer to the document cam. Okay, find the coordinates of the point of intersection of the line, blah, 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 with the plane, blah, blah, blah. Okay. This is actually pretty easy here. I hope you solved it with no problem. So here's our plane is x minus 2y plus 3z equals negative 1. Okay. Now, the parameterized form of the line was x equals what? 1 plus t. T ranges through all real numbers. So if that line intersects this plane, then there must be some value of t here. I'll call it t1 maybe, or you could just leave it as t. It doesn't really matter. But there is a specific value of t here for which what? That point is common between the two. So I would have 2 minus 3t1, right? Okay, plus 3z, that's always 4 plus t. So in this particular case, that'll be 4 plus t1. And that's the equation you have to solve to find the t1. Once you have t1, you go back and take that value and plug it in the formula up here for the line L, and you're done, basically. So this is pretty easy. I have 1 plus t1 minus 4, okay, plus 6t1 plus 12 plus 3t1 equals supposedly negative 1. Okay, so let's see, let's gather the coefficients together, like terms together. 12 minus 4 is 8, plus 1 looks like 9 to me. Okay, then I've got 1 and 6 more makes 7, and 3 looks like what, 10. So I've got 10 t1s, and that's supposed to equal negative 1. Okay, let's solve for t1. I think we can do it in our heads here. It looks like t1 is actually negative 1 also, isn't it? Okay, that's a major result here. That's not my final answer, but I will circle it. Now, what is the x value then? 1 plus negative 1, so that's 0. Y would be 2 minus 3 times negative 1. That looks like what? 5. and z looks like 4 plus -1 is 3. So it looks like the point in common would be what? 0, 5, and 3. Now I'll box that in because I'm pretty confident that's the answer, but let's just double check here. If I did my arithmetic correctly, this point should definitely lie on the line, right? Because I used the formula for that with a particular value of t being -1, so I think I did my arithmetic correctly. And then the last thing you would check here is to see if this point actually lies on this plane. So see if it satisfies this condition up here. 0 minus 10 plus 9, when I substitute it in there, is -1. Yeah. Okay, so we're good. Alrighty. So the point of intersection should have been 0, 5, 3. I found a typo on this one. Should have been normal form. Okay. I use the term normal form. Your book uses like general form. The reason why I use normal form for a plane ax plus by plus cz equals d is you should be able to just look at that and read off a normal to the plane, right? The vector abc. Okay? Anyway, find the normal form of the plane orthogonal to the line x equals 7 plus 3t, y equals 2 minus t, z equals 5t that contains the point 1, 4, 3. Okay, so this isn't much problem here. This is pretty easy too. Okay, let's do the following here. The idea that we're going to use here is the plane's supposed to be orthogonal to this line. So that means any vector that's parallel to the line will act as a normal to the plane, which is just what we want here because we're looking for the normal form here. Okay? So if you've got a point and a normal to a plane, you're in business, right? Okay? Well, wait a minute. If you look at this, the equation of this line, you can see, let me write it this way. This would be a vector form of the line, just to help you here. This would be, 7, 2, 0. Okay, that would be a position vector of a point on the line, plus all scalar multiples of 3, -1, 5, right? Alrighty. Now, can you tell that this vector, I'll call it v for the moment here, this vector v is actually parallel to the line, right? 3, -1, 5. But that then would be what? Since that line is orthogonal to the plane, this would actually act as a normal. So a better name for it rather than v in our context would be what? N. So I'll call that n for normal, and I've got 3, -1, 5, so this problem's easy. Now you remember how it works here. Once you've got a normal and you've got a point, then it's going to be easy. You just go like this. Well, the normal dotted with what? A vector from the point P to any point x, y, z on the plane must have a dot product that's 0, right? So that would be what? X minus 1, right? Because the point is 1, 4, 3. Y minus... Okay, did you guys get that? Okay, my frame stopped on my... Anyway, okay, so this is it. Now when we take that dot product, we would get 3 x minus 1 minus y minus 4 plus 5 z minus 3 equals 0. Okay, so that's 3x minus 3 minus y plus 4 plus 5z minus 15 is equal to 0. Okay, so that's 3x minus 5z equals 14, I believe. Okay. Okay, I think I did my arithmetic correctly. Okay, there's number 4. Do these two lines intersect here? Okay, well, t ranges through all real numbers and w ranges through all real numbers here. So the easiest way to solve this would probably, if they do intersect, then the following would have to hold, that there's got to be a value t1 and a value w1 such that this holds. If you didn't want to use the subscripts, that's okay. You could just use t and w, but my point is there's a particular value of t and particular value of w for which this holds, because those are both the x value, right? And it's supposed to be this, if they intersect, this is the common point between the two lines. We would have this holding, and we would have what? Let's maybe do this here. The y's would be equal, so that would be what? 3 plus t1 equals negative 2w1. I'll put a colon there. And then the last one, negative t1, would have to equal 1 plus w1. Okay? Okay? Now you notice here that there's a possibility that this is not going to work because I have what? 3 linear equations and 2 unknowns. You know, sometimes that doesn't work out, right? Okay? But if it does, I think we can solve it pretty easily. This is probably the easiest way to approach it. There may be other ways to approach it. In fact, there are, but I'm not going to bother here. I'm going to take what I think is the easiest way. I'm going to take the first 2 equations, because they're 2 linear equations and 2 unknowns. We ought to be able to solve that. And then we just need to see if the values we find actually satisfy the third equation. Okay? I'm going to just use the addition method here. So I've got 1 minus t1 equals 2 plus w1, 3 plus t1 equals negative 2w1. If I add these two, I would get on this side 4. If I add on these side, on this right-hand side, I would get 2 minus w1. That would imply that w1 is negative 2. Okay? What would the corresponding t1 have to be? Well, back substituting here, it looks like 1 plus negative 2 is negative 1, so t1 would have to be 1. Oh, wait, I should come up here to this one. I blew it. Like, this should be substituted in either one of these. So let's come up here and substitute it in here. 2 plus negative 2 is 0. 1 minus t1 is 0. Implies t1 is 1. So it still works. You notice if I substitute these values in this third equation, it still works. So there is, in fact, a point. Let's just say that. Let's write it here because you need to do it, really. Check. Is it true that negative 1 equals 1 plus negative 2? See, I'm checking with the third equation here, since I used the first 2 to find these values of t1 and w1. Is that true? And yes. So, in fact, there is a point in common between these 2 lines. How would you find the rest of it? Well, take a value, either t1 or w1, and stick it into one of them, or both of them, and you should find a point. You can double check here. I'm going to have t1 equals 1, so I substitute in here. X would be 0, right? 1 minus 1 is 0, maybe. Y is 3 plus 1 is 4. And z would be just negative 1. So it looks like the point would be 0, 4, negative 1. And you can double check here. If I let w equal negative 2, I get 0, 4, negative 1 also. Okay, so it's this particular point. So they do have a point in common. Okay, I'm going to stop this right now and do this in 2 parts because I'm not sure if this first part even worked out for the recording. Okay? Okay, I guess the first half did work out. Okay, I was just looking through it here. I'll move this up closer though. Hopefully you guys can see better now. It says find the distance from the point 0, negative 1, 5 to the plane x minus y plus 3z equals 12. Okay, if you remember the formula, the distance, let's say the distance is d. Okay, I'm going to use a big D. The distance from the point x naught, y naught, z naught to the point, let's do this, ax plus by plus cz equals little d. Okay, and you're talking about a point x naught, y naught, z naught. Okay, the distance from this point to that plane will be the following. Okay, so they showed this in the book. You break it down. It's pretty cool here. You basically just evaluate the expression in x, y, and z on the left at the point x naught, y naught, z naught, and you take the absolute difference from that computed value with d, and then the last thing, you divide by the magnitude of the vector, the normal vector, so that would be a squared plus b squared plus c squared. Okay? Alrighty, so there you go. Now, the way you can do this with projections and stuff like that, you can do this, but this is what it boils down to. Okay? So we prefer this shortcut. By the way, this formula's in that sheet I put up on in Canvas announcements, some useful PDFs or whatever I called it. Okay, well, let's work this particular problem. So now it's pretty easy here. I got the absolute value of, okay, so I've got 1 times, what, 0. My b here is -1, right? -1, I'll just write it that way. Subtraction minus y naught. My y naught is -1. Okay, plus, oops, that's supposed to be a c in there. You guys probably saw that. Okay, right in there, c, ax naught plus b, y naught plus c, z naught minus d. Okay, my c is 3. Okay, what's my z naught? 5. Okay, now what's my d over here? That is 12, so I'm subtracting that, 12 from that. And then I'm dividing by the square root of, make sure you get the right one. Don't find the magnitude of pretending that's a vector or something. Find the magnitude of the normal. So that's going to be what? 1 squared plus -1 squared plus 3 squared. Okay? And the rest is arithmetic. Okay? What would that be? 15, 3, is that 4 on top? Okay, down here, you've got the square root of 11, I think. If you like rationalized denominators, you can multiply in the numerator and denominator by the square root of 11. Okay, let's see what that's approximately equal to, actually. Divided by, I didn't ask you to do this, but that's about 1.206. Just for curiosity's sake, I like to see the decimal. Okay, 1.206 units, whatever the units were. Okay, anyways, there's number 6. Find the angle of intersection of the planes below to the nearest 1/10 of a degree. Okay, so notice I boldface that. Students have a tendency to just forget, that aspect of it. Do you remember the angle between planes is what? The angle between their normals, right? Okay, what's a normal for the first plane? I'll go normal 1. Well, it's x plus y plus z equals 3, so the normal would be just what? Picking off those coefficients, 1, 1, 1. How about the second normal? How about 1, -1, 5? Okay. Now, to find an angle between any two vectors, what do? You use this fact, right? The dot product of the two vectors is the magnitude of the two vectors times the cosine of the angle between them. Now, when we use this, we're going to use cosine inverse to find theta, and that's going to be perfect because whenever you have two vectors, you could think of two vectors this way. They're free vectors, so we can move them to the same initial point. Now you have an angle this way, and you have an angle this way. Which angle are we interested in when we talk about a unique angle between the vectors? We're talking about the smaller of the two. So you can see this angle is larger than this one. Okay, so we're just talking about an angle between 0 and pi radians. Or in this case, since we're talking about degrees between 0 degrees and 180 degrees. When you take a cosine inverse, if you think about the range of values the cosine inverse will give you, it's between 0 and 180 degrees. So this is perfect here. Let's take the dot product of these two. So that would be what? 1 times 1 is 1. 1 times negative 1 is negative 1. You want to add these up. 1 times 5 is 5. So add those up. And that should be what? The magnitude of 111. We could do that in our head and see that's the square root of 3. The magnitude of the other, let's see, that would be 1 and 1 and 25. That's 27, isn't it? Times the cosine of the angle. Okay, so this would be 5 over the square root of 81. So that's what, 9, right? Okay, so that's the cosine of theta. So theta is going to be the cosine inverse of 5/9. And you want this in what, degrees, I asked? Okay, so cosine inverse, let's do it in my calculator here. I get 56.3 degrees. Let's do this again. 56.25 degrees, and you want it round to the nearest tenth, so it's 56.3 degrees. Okay, at least that's what I got. Alrighty. Right, so that one wasn't bad. Find the volume of the parallelepiped formed by these vectors. Do you remember the volume of the parallelepiped could be written this way? It doesn't matter what order we do this in, by the way, but it could be this, the magnitude of u cross v. When I shouldn't say that. It's the absolute value of this. Now notice the cross product is going to be a vector. W is a vector, so when I take the dot product, I get a scalar, right? It's a number. I need these absolute value signs in the end to talk about a non-negative volume. Okay, so it's very easy here. We just go u cross v. Let's see what we would get here. I'll use my determinant-like formulation here. Okay, I've got 1, 1, 5 and 4, 2, 5. Okay, so I'm treating that like the determinant. Okay, my I component would be what? 5 minus 10, which is negative 5. My J component would be, don't forget this is backwards, that's what? 20 minus 5 is 15, positive 15, not negative. And this one, when I do that, it's going to be what? 2 minus 4 is negative 2. So there's the cross product that I got. Okay, so I hope I didn't make any arithmetic errors or anything. Now, I don't want to divide any scalars out of, well, you could, but you'd have to retain the scalar on the outside here. It isn't like finding a normal, right? Okay, this is going to be used to compute a volume, so don't monkey with it too much here. Now what I need to do is do this. Oops, why did I put a dot there? I want a dot now. Okay, I want to take the dot product of this vector with this vector. So I'm going to go like this. Okay, I'm going to post these solutions also for you, so you'll have hard copies in case, you know, this video didn't work out for you or whatever. Negative 20 plus 30, I think, minus 10. Okay, I think I did that right. And what did you end up with? Did you get 0? Okay. Did you get 0? You know why? Because I stupidly used the wrong vector there. I can hear you guys screaming at me out there. See, what I needed to do was this. Okay. You could have 0 volume, but that would mean what the third vector is lies in the plane of the other two. So my W is in fact what? 0, negative 2, 3. Okay. I'll clean this up when I actually do it there. So we get what? 0, negative 30. Okay. And then what? Negative 6. Okay, if I'm doing it right this time. Okay. And it looks like negative 36. Now the volume's going to be the absolute value of that, isn't it? Equals 36. Is that what you got? Did you get 36 units? That's what I got. Okay. All right. If I made any arithmetic method errors, the method's correct anyway. Okay. All right. One more question to go. A projection question. Okay. So these are usually pretty easy. Okay. Do you remember if I'm going to project V onto U, that's going to be what? A vector parallel to U, first of all. So it's going to have what? It's going to be a scalar multiple of U. Okay? Now what scalar multiple? Do you remember? It's going to be U dot V or V dot U, doesn't matter. Okay? Over U dot U, like that. Okay? This is also in that formula sheet I mentioned. Okay, but you should be familiar with this by now. Okay, these are just two vectors, right? I and j components only. This should be pretty easy. Let's take the dot product of the two. Negative 1 plus 14. That's what I get upstairs here. U dotted with itself would be what? 1 plus 4. Okay? And that's going to multiply on U, which is 1, 2. Okay? So that's negative 13/5 times our vector 1, 2. So that would be what? Negative 13/5, comma, negative 26/5, I believe. And we box in our final answer. So there you go. There's the quiz one.